So from last time we did a separation of variables. The y stuff got on one side with the dy, everything else on the other side with the dt. We integrated. We didn't need the absolute value. Why was that?
Because the body temperature is
The body temperature is already greater than 60 and it won't go below 60. So we don't need the absolute value, and then to get rid of the natural log, we make a base of e on both sides, and we wind up with y minus 60 equals e to the kt plus c. The exponent can be simplified by breaking this whole thing into two like bases being multiplied together, which is what we did here. And because e to the c is just a number, it's a constant, we turn that into a constant times e to the kt, which is where we came up with that. Then we had this minus 60 over here, so we added 60 to both sides to wind up with y equals c e to the kt plus 60. That's like the basic part of this equation. Notice the parts of this. This 60 right here is not coincidental. That's the ambient temperature of the room. Okay, then we had two ordered pairs, 0, 100. And when time started, when we measured the body's temperature, it was at 100 degrees. 10 minutes later, right? Yeah. 10 minutes later, the body's temperature was at 90 degrees in this room that's being held at a constant 60 degrees Fahrenheit. So, okay.
So this body is dead.
Dead.
But we didn't kill it.
It was dead
I
before we
know,
got
but
there.
It was dead before we got there.
Why would the body temperature be higher than normal?
Maybe they died in a microwave.
Yeah, maybe they were trying to get
Okay. Okay, I just was wondering if there's like reasoning.
So this is a basic problem. You're absolutely right, but this is a basic problem that deals with easier numbers so that we can focus on the ideas and not worry about complicated numbers. Okay?
Okay, that, I didn't know it
Yeah, it's a made-up problem.
was that.
Okay.
Wording like
Sort of made-up problem.
fevering and he's dead. How was that even?
So then this is with a time of 0, that's an initial value. You plug in the 0 for t, and you wind up with e to the 0, which is just 1. So then you have c plus 60 equals 100. Subtract the 60 from both sides, and therefore c equals 40. So that's where we came up with that. So now we substitute that in, and we need to find k. So to find k, we use the other ordered pair, plug in those numbers, and now we're just solving for k. We subtracted the 60 from both sides and divided both sides by 40 to get the 3/4 equals e to the 10k, and that's where we had to stop last time. So what do we do next? So that's going to mean we natural log of both sides, and I wind up with the natural log of 3/4 divided by 10 equals k, and we can enter that into our calculators to get a value. Because this body temperature is decreasing, I'm expecting my result to be negative.
In this case, would it be horrible to use the natural log of 3/4 and natural log of
No, 3/4 is 0.75 exactly, so you can do that.
So it's better to do that.
Sure, if that's what you prefer.
Sometimes I just do fractions.
7, 6, 8, so 7, 7 is what I'm going to write there.
Why are we rounding?
We're not rounding. We have to round when we write that k value written out like that. But when we use our k value to evaluate this problem to come up with our final answer, if that's what we're supposed to do, then we would actually not use the rounded, remember from last time. We'd either use this right here, or we would use the calculator's answer, depending on what it was that we were doing.
So now we take that k and we put it into the line.
Right, so now we have an equation. We have y equals 40 e to the negative 0.02877 t plus 60. Okay, now the problem says how much longer will it take for this temperature to decrease to 80 degrees Fahrenheit. So what do we need to do? We're looking for T. Yep, how much longer? That's a time, so it's 80. Because the body temperature needs to be 80 equals 40 e to the negative 0.02877 T plus 60. We can do some of this math in our heads.
Minus
Subtract 60 from both sides, and now I got 20.
divided by
Divide both sides by 40, and I have 1/2 equals e to the negative 0.02877t. So the natural log of 1/2 divided by, yeah, if you want to go back to what k actually is, I'm going to write negative 0.02877 here to get t. But then we're going to type, we're not going to use this, we're going to use the calculator's answer for this, or exactly this entered in again. What do we get? 24.09
hours.
exactly?
Days. 4 days.
Okay, so 24.09 for blah, blah, blah. So 24.09 minutes. But what is that?
Minutes more.
Is that minutes more?
Yeah. No, it's 20.
That's minutes from the beginning of when we first measured the body. So to answer this question the way that it's written, minutes more means that we need what? Yeah. Right, so I'm going to write, 14.09 more minutes. This is a very fast cooling body.
Maybe it wasn't kind of minutes back then.
So that would be your answer right there. But the main thing here, the important thing that happens every time on a Newton's law of cooling type problem is this first part where you go from this to generating the equation. And then from this, you do exactly what we had been doing with problems like this, where you find your C and you find your K using two original given pieces of information. Then you can solve.